we gonna keep kicking. And in 5.3, which is where we're looking at today, let me adjust that because it's thinking I'm way too loud. Check, 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 check. Cool. All right. So for 5.3, we are going to be looking at two more centers that we're going to get out of these. Now, I'm just going to give them here, and then we'll spend like a little section on each of them. The first thing that we're going to be looking at, we're going to be talking about centroids. And we're going to be talking about orthocenters. Okay. Now, the centroid is legitimately what I consider to be like the most useful out of all of these. The other ones can be useful, especially like if you're trying to design like a park or a plot of land and you want stuff equidistant. Like it makes sense that if you had a triangular shape, you want to know what's equidistant from the sides. Maybe you want to have entrances there, or maybe you have entrances or porta potties out at the like points, and you want to be able to know where should I put these in the case of like a big event so that they're equally distant from everywhere. You're shaking your head, but realistically, maybe, right? Like you've never had to plan a big event, but do you think people, when they do big events, like imagine a huge outdoor music festival, do you think they put a lot of thought into where the porta potties go and where the concessions go? You better, or else you're going to have a mess on your hands. And somebody has to think about it, and somebody has to do the geometry to be able to get the right answer. Now, as we're doing stuff, the centroids and orthocenters, these come from two more special segments that we get in triangles pretty consistently. So for no reason other than it's written first, we're going to talk first about centroids, but it's not what I'm going to write initially. We're going to talk about medians. It says centroids and orthocenters. All right. So I'm trying to make it so it doesn't sound like I'm talking into a tin can here. Okay. So as we're looking at this, median, you guys have seen that word before, I think. But you've probably seen it with statistics. We are not doing statistics, but it's in the middle. Now, the nice thing is that if we took all of your test scores, whatever's right in the middle of that data when it's arranged, that's called the median. And is there a similar idea what's right in the middle of a segment in geometry? So it could be a bisector. Love it. But it's the midpoint. And you're not wrong. You are correct. The midpoint does bisect. So when we're looking at the median, we're just going to say with regard to a triangle is what we're talking about in here. The median is simply the segment from, we start at a vertex of a triangle, and we go to the midpoint of the opposite side. Okay. From the vertex to the midpoint of the opposite side. Now, I try fairly hard when we're doing lesson stuff. I try pretty hard to make it more of a discussion than it is just me talking at you guys. And whether or not you recognize that, I don't know. If you haven't yet, you might today because, bless you, twice, I think. I'm going to do more talking today only because I want to make sure that more people are here for as we're going through this. I'd rather try to get through the stuff quickly and make sure that everybody sees it in hopes of testing things going a little bit better. But if it gets too dry and too boring and it's just too much of me talking, please let me know. Okay, so as we're looking at this, it turns out that we have three medians. So I'm going to sketch a triangle, and I want you guys to sketch a triangle. And if you draw it nicely, and mine's not going to be super nice, but I'm going to make it, yeah, that's nice enough. I'm going to draw it here, and I think we can probably make the claim here that this triangle has three sides. Can we all just agree on that for now? Like, obviously, right? Now, what is the difference between a median and a perpendicular bisector? Because I think a median should bisect it. What's not included here, though? The right angle. We have no reason to think it could be perpendicular. Is it possible that we could have a triangle where the median is the perpendicular? Yeah, it'd be an isosceles triangle and drawn from that top angle. It's going to be the same on both. Now, as we look at this, for no reason, I'm going to say here is A and B and C, and I'm going to eyeball on mine, and I want you to eyeball on yours the midpoint of each of these three sides. So let's see. I bet it's there is my guess. Which do go up? 8. So 1, 2, 3, 4. Okay. So I think that's that midpoint. I think that's the midpoint here. And I think that's the midpoint here. Okay. I have the fortune of having graph paper or grid paper on mine, so I can connect mine. I think they're all pretty close to okay. I'm going to draw a median. And let's say we draw this one, and we'll see that that is BD. And if this is indeed a median, what do I know point D is? The midpoint, which means this and this ought to be the same. Okay. Can I draw another median? I'm going to draw AE here. And I'm going to just pause here before we draw the third one. And I know that you guys are sketching them. If you've drawn an isosceles or an equilateral, you're going to get maybe a misleading picture. But before I draw the third line, what do we call it when lines all meet at a single point? There's a specific word. It's a point of intersection. But what if it's for three? We use a word better than intersection. Concurrency. Before I draw this last line, do you think it's going to cross right through the middle? It looks like it's going to. Let's see if it is a single concurrent point. Klein. Hustle. Okay, if I draw the last one, and I'm just going to call this CF. Hey, mine's not perfect. It's close-ish. I'm going to make my point there, and we'll just draw it bigger. We have a single point here. Now, if we'd spent time to do this like super perfect, it would be very clear that this is the case. I'm going to name this point right here G, only because that's the letter that we have left. Now, we have constructed a single point of concurrency for all the medians. And this is always going to happen. They're going to meet at a single spot. Now, the other ones are nice because we can think about them from a circle. We can think about the circle inside. We can think about the circle outside. There's nothing to do with a circle here. Like, no part of this is dealing with the circle. Now, couple little things about this. I've said the word now about 50 times today, and I don't know why. And by today, I mean this hour, which is odd or not. Okay, we are going to make a couple little comments. Point G, this one, it is the point of the concurrent point for all these medians. Same place. Point G has a name. Point G is called the centroid. So we're going to say G is the centroid of triangle ABC and is formed from point of, and I'm going to say concurrent point is what I'm going to say. Concurrent point of the what's? Good. Of the medians. That probably should have been capital, but I'll underline it here. So point G is my centroid. Now, point G is the concurrent, or the point of concurrency between the three medians of a triangle. Pro tip, if I know that all the medians are going to meet always at the same point, do I really need to draw all three of them? No, with just two of them, I could have got that point G just as well. Two of the three will suffice. That's enough. Everybody okay here? Now, the theorem. There is not an intuitive part of this, especially as we just start looking at it initially. But check it out. I'm going to give you like 20 seconds or 30 seconds to chat with your neighbors. Is this halfway across the median, do you think? Does that look like halfway? Okay. Does it look like it's the same distance from here to here and here to here? No, gosh. So it's not equidistant from the angles. Makes sense. It's, you know, not the in-center. Or, sorry, circumcenter. It's not equidistant from the sides, which also not the in-center. What do you think? There's a special relationship here. It is not intuitive. What do you think, Sonny? Okay, 30 seconds. I want to see if you guys can come up with it. How much of the way across any of these medians do these distances go? And it's a really broad question. I'm going to give you 30 seconds just to see if anybody comes up with something without a whole lot of guidance. I'm going to give you 30 seconds. I'm going to walk around. When I pause it, I want to hear chaos and talking about the geometry. Go. I didn't pause it. Sorry. Just to one group. Anybody have, with except for Ronaldo and Rogue, any thoughts on what important thing that my centroid might do? So I agree with you, but we're going to word that differently, like kind of differently. If I kind of put this here, do you guys agree this is the entire length of the median? And I just want you to blindly guess. How much of this is that? That looks like 1/3, right? And if that's 1/3, this must be 2/3. Now, it looks like it, and we can measure it. It turns out you are correct. You have just identified the theorem. Now, we'll get that theorem out here in a second. I'm going to write one more little comment about the centroid. The centroid, for anybody who might want to do a little bit of woodworking, if I wanted to make a fancy triangular shaped light, and I paid a lot of money for it, and I'm just going to pretend with my hand here. Let's say I hung my light up, and then when I let go of it, it tilted like this. I'm going to be pissed, right? Like if I spend good money on a fancy light that's triangular shaped and modern and it tilts funny, it's going to be annoying. Turns out that this point is exactly where we would hang it. This is our center of mass, or how you would balance a triangle perfectly. Like perfectly. So we'll just make a little comment, centroid equals, and we can write center of mass. For freshmen, I kind of doubt, have you guys talked about centers of mass in physical science? Okay. Center of mass, or if you don't like that, we'll just call it the balance point. Now, there are some assumptions being made here. We're assuming that whatever material we're looking for is the same width, like it's the same volume everywhere, and it's the same density. So if you have a knot on one side and a knot on the other, they're going to be different densities. They're going to weigh less. It won't be exactly there. But in your theoretical perfect triangle of equal density, it's right there. Now, our theorem for the centroid, pretty chill. And you guys have kind of already identified it. People get goofed up on the direction thing, but we're going to see if we can't clean it up. So here we are. And what color was I doing this one with? Orange. We are going to jump right into, we're talking about medians. Cool. Let's give ourselves theorem 5.7. And theorem 5.7 is going to be our centroid theorem. Okay. This one, I'm going to try to be a little bit less wordy. How do you find the centroid? It's where the what's meet. Medians and vertices, the midpoint and vertex is median. So where the medians meet. Cool with that? The median's concurrent point is called the centroid. Cool. Where my medians meet. So I'm not going to sneak that in this theorem then. Here we go. Given a centroid, and I'll even use this picture here. Given centroid G, which just to really clarify, it's no different than me saying, if I give you a triangle and there is a centroid, it's the same thing. If and given means like the same situation here. If I give you a centroid G, especially on this triangle, then it breaks each median into fractional parts. So there's our first thing. And that shouldn't be a shocker because I could put a point anywhere on this. And unless I pick some weird value like pi, I'm always going to be able to get fractional parts. Okay. Fractional parts. We have a little bit more to say. Specifically, and here we go. From vertex to the centroid. And I'll scroll back up so I can look at those. Equals something. Does it cover more distance to go from a vertex to the centroid or from the side to the centroid? Is it always the vertex? Always. So do we all agree that from the vertex to the centroid is a longer part? Okay. It turns out that this is always going to be 2/3 of the median. Of median length. Or median's length. Every single time. Now, the fraction stuff, I think that I like to talk. I can't speak right now. We're going to try again. With fractions, not everybody loves them. But if this is 2/3 of the way across, or the way across, and I know that I need to get the whole way across, this must be how much of the way? 1/3, because 2/3 and 1/3 make 3/3, the whole. Okay. So with these, if vertex to centroid is 2/3 of median's length, how do I word the other side of it? So we can say side, or we could be, and I agree with you, but could I say midpoint to centroid is equal to 1/3 of median's length. Okay. Last little piece, and we're going to see this when we do an example problem here in a moment. And I lied. We're just going to write it here. I'm going to leave one little spot in case you want an additional comment. Let's get an example. So here we go. 5.7, there it is. Let's do an example of the centroid. Centroid. Cool. What I want us to do is we're going to find a segment for some specific triangle. And I'm just going to assume that the point we're given is the centroid. I'm only going to draw one median just to make this problem go a little bit quicker. Let's take a look. On this first one, let's draw a triangle. It doesn't have to be perfect. And what do you want me to call the centroid? What point is it? One more time. As in Victor? Delta and Charlie. So I'm going to go to the midpoint here. And I'm going to put the centroid, and it's roughly going to be here. We'll just call this C for centroid would have made awesome sense, and that's probably what you meant in hindsight. We'll call this R. That makes sense. Okay. We have a single median drawn. We'll make sure it's clear it's a median. And I'm not going to draw the other one, but we're just going to make the claim R is centroid of our lovely figure. Okay. Here's what I want us to do. We're going to say if RC equals, I'm telling you it is. Yep. Now, it's a good question, and just to be clear, your book will either do this or they'll give you something else here, and they'll say, hey, look, it's where the medians intersect. And then you'll have to reason out that it is. But I'm okay to just tell you for this one. But good question. If RC is, I don't know, what do you want RC to be? 12. 12 units. Find, and we're going to have two little parts. And I just, instead of doing A1 and A2, we'll just say find. We know RC is 12. I want us to find DR and DC. Now, we have a wonderful, wonderful theorem here working this out. Here's my challenge. The only thing that's not showing on the board is that it says centroid theorem right up here. I'm going to give you guys about 90 seconds. I want you to see if you and your neighbors collectively can work through this. Don't just blindly write an answer. Talk it out. If you have no idea what to do, check with your neighbor. If nobody does, check with me. And if everybody has to check with me, then we'll obviously talk about it as a whole. But I want you guys to try this first. If I tell you that R is a centroid and I give you this length, how do we find the other ones? Okay, I'm going to pause it, and we'll come back together in about 90 seconds. Talk it out. As we look at this problem, and I'm going to pull everybody back together here, there are two trains of thought that one might take. Now, right off the bat, one of these, depending on how comfortable you are with fractions, one of these might feel weird. What's twice as much as 1/3? 2/3. That is, if it's obvious to you, awesome. If it's not super obvious, you can still do these problems. As soon as I recognize that connection, whatever this distance is, R to C, this is always going to be twice as long if it's 1/3 and 2/3. Always. Right? And it's strange when we see it, but not everybody can see that right away. That's okay. If we wanted to do this problem differently than just saying, yep, it's just double it. First thing that I would do, because I have a picture, is I'm going to label it 12. Okay. Now, if you don't like the fraction stuff and saying, oh, what's twice this, or why is it twice, or you don't get it, there are other ways to go through. Do you agree that 12 is the distance from the midpoint to the centroid? And that's how much of the entire distance? Do you guys agree that this is still true? This distance is 1/3 the whole median. which is exactly what this says here, right? Could I solve this for DC? How do you undo a multiply by 1/3? Or if you'd rather, and I would, I think about this as dividing by 3. What undoes divide by 3? If we multiply both sides by 3. So times 3 and times 3, I get 36 equals DC, and I'm good there. Now, if I know the entire distance is 36, we'll work this way. I now know that DC minus 12 would give me DR, and we have to get 24. Okay, it doesn't matter which way you think about it. If you're okay with using the theorem here, awesome. If you'd rather use the fact that this is always going to be half of this, or that this is always going to be twice this, which is the same statement, just gone the other direction, we can work it out either way. Are these wildly challenging? Okay. We have one more that's not as nice. Okay. Today is Monday, right? You guys loved algebra. What just happened? Oh, Rafa. Okay. Weird. So everybody loved algebra. That's what I just gathered. Good. Okay. I'm going to draw a triangle here, and you guys are going to help me figure out what's the only, or at least find another segment we haven't talked about. Do not sketch the purple triangle, okay? Okay, so I have this obnoxiously large triangle. You do not have to sketch it. Check it out. We have constructed a few different pieces. We've dealt with the angle bisectors, which seems natural they can intersect. What is this point called? The incenter. Okay, could we perpendicular, and I'm not really doing it just so you know, could I perpendicularly bisect all 3 sides? And in this case, it's not going to be perfect, but they meet at roughly there, and that's called the what? Circumcenter on this one. Okay, the circumcenter. And then we said, hey, well, if we're just drawing lines and stuff, well, maybe these make sense too. And whether you've really dealt with medians or not, like they're of the same type, right? We're looking at special segments that we can draw in triangles. Unrelated, it's going to feel. How do you find the area of a triangle? 1/2 base times height, or base times height divided by 2. However you want to think about it. Do any of these necessarily represent the height? If I wanted to find the height of this triangle, how would I do it? Like, let's say I wanted to find the height. And we'll just draw it here. And like maybe it's an angle bisector, and that's kind of a harder question. Could I draw the height from point B? Now, if this was like a building and we just lived in 2D space and I hung a line, is it going to drop down like this? No. How's it going to drop? Straight down. So it would drop straight down to here, and it would form a 90-degree angle. Do we agree? Now, this is perpendicular. Was it a bisector? No, it would have to be here if it were a bisector, right? Now, it might have bisected this angle, but that would be called an angle bisector instead. Do I have to draw the height of my triangle from that point B? It's the most natural choice, right? Because it's the way it's aligned. Could I draw my height from here, though? Now, I don't want to have to turn the whole triangle. If this were now the top, it would hang down. It would be perpendicular to this side, right? Is it perpendicular here? Is it perpendicular here yet even? It's getting closer. I bet it's like somewhere out here, right? Kind of looks like it would be. I think it looks like it'd probably be about here. Maybe. Yeah. Like it's not perfect though. And we can draw more obnoxious examples here in a second. But I could draw the height from there also. Could I draw the height from this side? And this one's a little bit nicer because I think it's easier to pick out. It's probably about here is my guess. Somewhere in there, right? It's not a perfect right angle. We could draw the height from all 3 sides. Now, I'm going to pop over to GeoGebra here in just a second. When I draw this with a perfectly 2-scale triangle, any gut feeling about what's going to happen with all 3 of these heights? Are they going to meet at one point, or like everything else has, do you think? Let's check. Okay, I will check. I'll get this set up for you. We are going to split this lesson into 2 different days. We're going to finish it tomorrow, but I'm going to give you some assignment to work right now. So my hope is that you have almost no homework to do this evening. If you know it's twice of that, I'm okay with it. Yep. Okay. So let's check it out here. I want you guys to do a short assignment. I'm going to add to it tomorrow, and I guarantee I collect it on Wednesday. Wrestlers or anybody leaving early, you will have to email this to me. I'm going to give us a nice triangle to deal with on GeoGebra so we can think about these more specifically. Here we go. I want you guys to do. So we'll call this homework 5.3. And you're going to find this bad boy on page 227. We did not even talk about a bell ringer today. Didn't even cross my mind. Mrs. Holloway's out, and yeah, she said you guys did awesome. She didn't actually say that, but it's clear that you guys did do awesome. All right. So here we go. I want number 7, number 9, number 16, and I think those are the only ones that we can do right now. I'm okay with those. 7, 9, and 16. You guys have 5 minutes, 6 minutes to finish these 3 problems. I think you can get it. Cool.